Make sure you have read the chapter in the textbook before you watch this video. Let's do a quick review of oxidation and reduction problems, so that we can use this information to look at the properties of electrochemical systems. In a previous class, we learned how to calculate the oxidation and reduction number for each element in a compound. Let's apply that process to an entire chemical reaction to determine which elements are being oxidized or reduced as part of the reaction. Take the reaction of elemental iodine and sodium chloride to produce sodium iodine and elemental chlorine. We need to calculate the oxidation numbers for each element in the equation. Starting with the reactant side, then calculating the product side. For the reactants, iodine is in its elemental form, so the oxidation state is 0. Sodium chloride is an ionic compound, so we can split the ions apart and use their charges. Since sodium has the positive charge and chlorine has a negative charge, we can assign them oxidation numbers of +1 and -1 respectively. If this is confusing, please make sure to review how to calculate oxidation numbers from the text. Now, we can calculate the oxidation numbers for all elements in the product side. Sodium iodide is ionic. We can split it into ions. Sodium has a +1 charge again, so its oxidation number is +1. Iodine has a negative charge, so it has an oxidation number of -1. Chlorine is in its elemental form, so it has an oxidation number of 0. Iodine on the reactant side has an oxidation number of 0, but it has an oxidation number of -1 on the product side. This means it has been reduced. Chlorine has a reactant oxidation number of -1, but on the product side it has an oxidation number of 0. Thus, it has been oxidized and lost electrons. That is, its oxidation number has increased. Let's look at a slightly more complicated version. Take the decomposition of sulfur trioxide into sulfur dioxide and oxygen gas. Let's calculate the oxidation number of all the elements on the reactant side. We have 1 sulfur for 3 oxygens. They have a combined charge of 0, so the sum of all the oxidation numbers in that molecule is 0. Oxygen in compounds generally has an oxidation number of -2, so the oxidation number of sulfur plus 3 times the oxidation number of oxygen is equal to 0. Thus, the oxidation number of sulfur calculates out to be +6. So, for the reactant side, we have 6 for sulfur and -2 for oxygen. On the product side, we have sulfur dioxide, so the oxidation numbers are sulfur plus 2 times the oxidation number of oxygen equals the total charge, which is 0. In compounds, oxygen is -2, thus we have sulfur plus 2 times -2 equals 0. This calculates out to sulfur being +4. The oxygen in the elemental form is equal to 0. So, for this equation, oxygen went from a -2 in sulfur trioxide to a 0 in the elemental oxygen. Oxygen was oxidized, and sulfur, which went from 6 down to 4, was reduced. Now that you know how to calculate the oxidation numbers and states as part of chemical reactions, we can take a shot at balancing redox reactions that occur in acidic solution. Let's take a look at the nitrate ion reacting with solid copper metal to make nitrogen dioxide and copper 2. First, we need to decide which of the 2 species is being oxidized and which is being reduced. We can calculate this as we did in the previous example. We can also see that copper is being oxidized because on the product side it has lost 2 electrons. To balance an oxidation-reduction reaction, we can break it into 2 half reactions, the oxidation half and the reduction half. So copper is going to copper 2 is oxidation, and nitrate going to nitrogen dioxide is the reduction half. We don't have any oxygen or hydrogen to balance on the oxidation side, so we will balance the charges with electrons. On the reduction side, we need to add water to the product side to balance the oxygens. Then, we need to add 2 H+ to the reactant side to balance those hydrogens. Finally, we need to add an electron to the reactant side to balance the charges. Next, we check the number of electrons on each half reaction. They need to be the same, so they will ultimately cancel out. Since the oxidation side has 2 more electrons than the reduction side, we need to multiply the entire reduction half equation by 2, so the electron counts are the same. Great, this balances the 2 halves. Now, we need to add them back together. We combine the 2 reactant sides together and the 2 product sides together. This allows us to cancel some things out. Which leaves us with our final balanced equation. A good way to double check that you did everything correctly is to verify that this equation does indeed balance out in the final step. Let's look at a slightly more complicated version of this process when nitrous acid reacts with permanganate to make manganese 2 and nitrate. Remember, if you can't directly see which species are the oxidation half, you will need to calculate that as we did in the beginning of this video. For the oxidation half, we have nitrous acid going to nitrate. First, we need to balance the oxygens with water, the hydrogens with H+, and the charges with electrons. So we've added 1 water to balance the 3 oxygens from nitrate. Then, we add 3H+ to balance the hydrogens of nitrous acid and water. Finally, we balance the remaining +2 charge on the product side with electrons. On the reduction half, we have permanganate going to manganese 2. For this, we need to add 4 water to balance the oxygens from permanganate. Then, we need to add 8H+ to the reactant side to balance the hydrogens from the water. Finally, we add 2 electrons to the product side and 7 electrons to the reactant side to balance out the charges. This will cancel out 2 of the electrons, leaving us with no electrons on the product side and 5 on the reactant side. Now, we compare the electrons from the oxidation half to the reduction half. They aren't equal, so we need to balance them so we can cancel properly in the final tally. To do that, we need to multiply the oxidation half by 5 and the reduction half by 2. That gives us 10 electrons in each half. Now, we combine the 2 halves by adding all the reactants from both to one side and all the reactants from both to the other side. Then, we cancel things out. In this case, 5 waters cancel, 10 electrons cancel, and 15 H+ cancel. This leaves us with our final balanced equation.